All right. Is it bouncing? La 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 la. All right. Is it bouncing? Okay. I will talk. Dear Father, we thank you for this day. And Lord, I thank you for the students. Just ask you to bless our class as we study topology, Lord. In your name I pray. Amen. So what I decided to do here in the first few minutes is just to try to kind of go through and pick up some various pieces. I will eventually get back to Gamelin and the next section. So we'll see where we get to here. First of all, I'm going to copy a homework exercise from Moncrief's topology, which has some claims in it, which I think are useful to be aware of. And so here it is. So we have, this is number 2 of page 18 in my copy. I think this is the second edition of topology. A thicker copy? Well, mine, thicker, hardcover? Yeah. I had that once upon a time, but then I traded it to my brother for some reason. He gave me some other book, and I gave him that book, and then I forget exactly what happened, but it made sense at the time. He gave me a first edition of Moncrief's, as I recall. He was then in grad school and needed the second edition because he had a class in it, I think. And so that's the story of how I lost my hardcover of Moncrief's. But I think I did it to gain a copy of the second edition of Bryce DeWitt's, Ryder's quantum field theory text, which had an extra chapter on supersymmetric field theory. It was useful to have. I digress. So these guys, subset of B, and so this says, show that the inverse, that F inverse preserves inclusions, unions, and intersections and differences of sets. So, fun facts, which we could prove if we were so inclined. First of all, if B0 is a subset of B1, that implies that the inverse image of B0 is a subset of the inverse image of B1. Good to know. Also, the inverse image of a union is equal to the union of the inverse images. I feel like we've quoted these results piecemeal as we've come to them. It's probably good to have a list of them. Intersection, also. So inverse images are nice, yeah? And, also the difference, also preserved. So if I had like B0 minus B1, that's F inverse of B0 minus F inverse of B1. Again, F inverse here is not a function. These are the inverse images as a set, right? I mean, F inverse might be a function, might not, I don't know, all right? And then in contrast, so these are all fun facts about the inverse image. Forward image, F preserves inclusions and unions only. So the forward image is not so nice. So A0 subset of A1 implies that F of A0 is a subset. Subset of F of A1. And the F of the union is a subset, equals F of A0 union F of A1. f of the intersection is just a subset of the intersection of the images. No equality here. And finally, difference contains the difference. It's not equals, but we can say that. However, there is some fine print which is worth writing down, which might have been relevant to something we were working on, all right? Which is what? So this one right here, we get equality if what? What's that? Injective, right. If f is 1 to 1, then we in fact get an equality there. And likewise, the next problem asks to show that the union, intersection, union, the next one says to, basically says that you can extend this from 2 to arbitrary unions or intersections. That's next problem 3 here. And then a variety of interesting things after that. But this is kind of the, yeah. Well, it says injective. It could be a typo, I suppose. Well, let's see here. So let's see if we can prove it, right? I mean, let's try to work on this one. Yeah? We haven't done too much of that sort of thing in here. Let's work on that. Let's see. Let's assume f is surjective and see if that helps us. Right. So f of a equals b, right? And what else are we supposed to do? Let a sub 0 a0 be a subset of a, right? And I think to make it interesting, we should assume what? A1 is a subset of A0, right? Otherwise, it's just a statement about the empty set, so who cares? Oh, I'll tell you who cares. People who want a complete and logically consistent characterization of intervals. The empty set is trivially connected. So I was wrong. There are 10 intervals of real numbers because the other interval is the empty set. There is disagreement about this, but my brother makes the case that we should definitely include it because otherwise everything you ever say about a connected set always has to be like, oh, and by the, you have to qualify. I mean, to reduce clutter, it is helpful to just agree that the empty set is a stupidly connected set, since there's nothing to connect or disconnect, as the case may be. All right. So to show equality, we're going to try to show equality, right? So we should pick a point. Let's suppose x is an element of f of a naught minus f of a1, right? Hence, there exists, let's say, little a sub naught in a sub naught, such that what? F of a naught equals to x, right? However, x is not an element of f of a1, so a naught apparently is not an element of what? I was about to say a naught is not in a1, right? I mean, isn't that immediate from what I'm currently doing, though? Am I okay for now?
I mean, if f is rather injective, subjective is not.
But doesn't, I mean, I have picked, there exists a naught and big A naught, such that,
It could be like some element outside a1 that passes to the original a1. That is also possible. F is not injective.
I'm sorry, I'm just not, so you're saying this does not follow at the moment?
I mean, because we do not assume that f is injective. So you know, like if you have a0 in a1, have a0
Because, I see, because I could have, otherwise, if f was not 1 to 1, I could have that there exists an a1 not equal to a0 with a1 in a1 and f of a1 equal to f of a0 equal to x, right? And I know that, but if I assume that f is injective, then I know that if f of a0 equals to x, and x is in f of a0 minus f of a1, that means x is not an element of f of a1. And there does not exist a1 in a1 such that f of a1 equals to f of a0. I think this is not being said very cleanly. Let's try this again. I mean, let me try to say what we're saying again more clearly. All right. So injective, we pick x in here. So thus, there exists A0 in big A0 such that what? F of A0 equal to X, all right? Can I say anything more about that A sub 0 at the start? Okay, so then without loss of generality, we well, I guess there's some cases to think about, right? If A0 is in A1, right? Which we're assuming is a subset of A0, right? So that's certainly possible. Then f of A0 equals to x is an element of f of A1, right? And that contradicts, let me give it a name, star, right? Therefore, A0 is not an element of A1. Hence, X, well, what can I say? Well, hence A0 is where? It's an element of A0 with A1 removed, right? And so, X is an element of what? F of A0 minus A1, right? Which I think is part of what we're trying to prove here. Namely that this is a subset of that given injectivity. Actually, I don't think I used injectivity here, did I? Not yet. Yeah, I think, so at the moment we've done what? We've proved this is a subset. I mean, we proved what's in the blue. We did not use injectivity, and we should hope that we don't need to use injectivity for this direction either, right? If we trust the exercise. So, but when we reverse this, is where we should need the injectivity. All right, so let's go the other way. Suppose what? X is an element of f of a, let me say y rather than x. Suppose y is an element of A0 minus A1. And f is 1 to 1. All right. Then there exists what? A little a in A0 minus A1, right? Such that what? F of little a is equal to y. I should warn you, this is very foolish what we're doing right now. We're trying to make me think today. Emily already knows this is very dangerous. It's true most days, but especially today. I mean, I guess you got choices, right? If A is an element of what? Okay, so this says we have that A is an element of A0, right? So thus, Y is an element of F of A0. Suppose Y is an element of F of A1. Then there exists A1 in A1 such that F of A1 equal to Y equal to F of A0. Or just used A this time, didn't I? Then by 1-to-1, A1 equals to A by injectivity, right? Therefore, A1 is where? Is an element of A0, which is kind of tricky because yeah, I mean A is in A1, don't I? Yeah, I want A is in A1. That's where the A is in A1. And of course, as we previously assumed, A is in A0 complement A1. Contradiction. Hence, the supposition was not so cuckoo. In other words, Y is not an element of FA1, right? And so Y is an element of F of A0 minus F of A1, which completes the proof because that shows that Y in that difference is also in that difference, which is the reverse inclusion. They have equality of the sets. And you can see that the injectivity was necessary to obtain the contradiction. This gives an alternative characterization of injectivity? Ah. If and only. So if this holds for all subsets, then that also implies injectivity. Interesting. Yeah. Okay. Anyway, I thought it would be wise for us to go through such an exercise because, I mean, these do make kind of like decent test questions, right? I mean, it's just plain set theory. A good part of what we're doing right now is just set theory. It would be a decent thing for me to give you a question where you can show me that you have taken the time to understand set theory, because that's something that you will have done if you've studied this course, right? I mean, so. All right. I shall erase. Next up, I was going to mention the pasting lemma, because this is useful to us. I've quoted it, but I don't know as it's ever quite stated in Game 1, at least not that I've noticed yet. And so I thought it would be helpful to us to steal a theorem from Moncrief for our various constructive purposes. This is his theorem 18.3, the so-called pasting lemma. And it simply says this: let X be A union B, where A and B are closed in X. For that to make sense, apparently X is a topological space, right? Let F from A to Y and G from B to y both be continuous, what else would you do? We never, come on, of course they're continuous. What else would we do? If f of x equal to g of x for all x in the intersection of a and b, then h defines all right. This is the pasting lemma. Shall we prove it? I think we should prove it. You can see why this would be useful, right? Right, yeah, we used it for the gluing paths together the other day ago. Yes, last time, that's right. So here's his proof. He says, let C be a closed subset of Y. He says you can see that H inverse of C is F inverse of C union with G inverse of C. He says, by elementary set theory. So I think what he's proposing there is that you can show that those sets are equal by picking a point in one side and showing it's in the other and vice versa. So let's see. Let's actually just think about that for a minute. So let's do some of that elementary set theory that Muncre's hides. Let's see here. Let's start with if x is an element of F inverse of C union G inverse of C, then what? Then either one, if x is in F inverse of C, right? Then what's that mean? Yeah, f of x equals to h of x, right? Because that would mean that it's in the domain of f. So the rule for h would be f of x. So x is in h inverse of c, right? And 2, if x is in g inverse of c, then g of x is the h of x. Therefore, x is in h inverse of c again. So any way you slice it, if it's in that union, it's in h inverse of c. And then conversely, if y is in h inverse of c, what's that mean? There's x and c such that what? Or did I get it? Am I wrong?
I mean, I think that it's,
I'm wrong?
I would think
You don't think that's true?
yeah, I mean, like, they upload the extent and they was from C, right? And you apply the FX instance. So this is still kind of good. Shouldn't be like HY.
It should be hy equals to x, right? But then remember that I'm sorry, guys. Brain not working at the moment. Sometimes I have to erase. All right. If it's the inverse image of C, what's that mean? What's that? So if y is in H inverse of C, then H of y is in C. But where did y come from? Right? And x was A union B, right? So what's that mean? Either y is in A, right? What's that tell me? If y is in A, H of y is what? Right? Which means that y is an F inverse of C, yeah? Right, yeah. 2 likewise. Which is to say that y is in the union of F inverse of C and G inverse of C, which is, all right. As he said, it really is elementary set theory. I mean, he's not joking. It's not even topology. Yeah.
You would have drawn two circles, x and y, and then you divide the circle that have x into part A and part B, and then just map.
You're saying I could combine the arguments?
No, I'm just saying it'll be easier to look draw. You get like a map from two circles. Circle one is topology x, and then you divide circle one, that circle into part A and part B. Then you combine equals x, and then you have another circle which is y.
Hmm.
The mapping from A to y is fx. The mapping from B to y is dx.
Oh, you're saying like if I put like a little sub A on the F and a little sub B on the G or something like that?
Yes.
It would be, yeah, right. That would, if the notation was more specific to the domains, I would see it more quickly. I agree. Yeah. Agree. Okay, that was just the entering gambit for the proof, though. Let's get back to, okay, so we have that, then what? He says, since F continuous and G continuous, we have F inverse of C and G inverse of C closed. Well, I've jumped the gun a little bit. I'm sorry. I'm an idiot. There's a relative topology thing in here. I got to be careful. Because it's, grief. F is continuous. That means F inverse of C is closed where? In A. Hence, also in X. Since G continuous, G inverse of C is closed in B, hence also in X. Consequently, F inverse of C good grief, union G inverse of C. So we got closed, right? Closed. What's the union of two closed sets? Right. The union of closed sets is, the finite union of closed sets is closed. Why does this prove continuity? Right, this is an equivalent characterization of continuity. And I think that is now is as good a time as any to rattle off what are the equivalent characterizations of continuity, right? Because we've kind of been, so that proves it because we've shown the inverse image of a closed set is closed. Do you understand what I'm saying here? Closed in A, hence also in X. Does that make sense what I'm saying? I'm saying closed in the relative topology. The subspace topology of A implies closed in the whole topology.
I mean, if it's closed in A, then X is a closed subset of X. That is
I need that A is closed in order to say that. Yeah. Okay. But following our equivalent, so if we have F going from X to Y, X and Y topological spaces, following our equivalent, number one, F continuous. And what was our definition of continuous here? The topological definition of continuous is that the inverse image of open sets is open, right? But likewise, if the inverse image of closed set is closed, if you have that for, I should, any. The inverse image of any closed set is closed, right? Then that is another way of capturing continuity. That's actually his 3. This is theorem 18.1 in Moncrief's for what it's worth. Another characterization too he has for every subset A of x, we have that the image of the closure is a subset of the closure of the image, is another way you can characterize continuity. And finally, 4 is the neighborhood definition for each x in x and neighborhood v of f of x. There exists neighborhood u of x such that f of u is a subset of v. Obviously, 4 to me feels closest to the epsilon delta definition, right? Although you notice it's not directly the epsilon delta definition either, because it's not written in terms of open balls. Even in the context of metric topology, 4 is not directly epsilon delta continuity. It's something else, right? So we were talking about that earlier today. Okay. Anyway, sorry, I'm kind of going back and hitting some things that we already talked about, but I think it's healthy to do this, yeah? Now let's do something weird. Sound good? So I'm going to hop over to Minetti, and I'm going to look at his example 3.11. Oh, I'm sorry. Probably should read that 311. So here we go. I'll just write things here for a while. Let K be a field. All right. So far, not too weird. Let N be an integer. Positive integer, I think, here. Yeah. And K, x1, x2, dot, 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 xn. What would that be? So he says polynomial ring in n variables. How do you add polynomials in n variables, guys? It's a ring, right? So that means that there's a way to add things and a way to multiply things. What is an arbitrary thing like? Hey, while we're on the topic, and to relax my brain for a second, what would an arbitrary polynomial look like? What's the formula for it? How about this? F of x equal to a sum I1 dot 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 I n equals 0 to infinity of C I1 I2 dot 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 I n x. Oh man. Yeah, finitely many non-zero, but I want powers of the x's, yeah? Oh, that's right. x1 to the I1, x2 to the I2. I got it. Xn to the In, where only finitely many, let's say c sub I, are not equal to 0. We just call this thing c sub I for this, right? This is a polynomial in n variables. If you add two such things, you get another such thing, because if there's finitely many one, and you add it to another that only has finitely many non-zero coefficients, well, the result is something that has finitely many non-zero coefficients. And you already know how to multiply these kinds of things, right? You just multiply according to the usual rules of polynomial algebra. And again, if they start with finitely many things, and you multiply it with something else with finitely many things, and you distribute according to the usual distribution laws, still finitely many things, and that's why it's a ring. It's closed under the natural addition and multiplication of multivariate polynomials. So it's a ring. Great.
On the head abstract, what's the definition of a field and a ring again?
So field, this means that this is a ring such that every non-zero number is a unit. This means has a multiplicative inverse. You say, well, what's a ring, right? And here, ring, I mean, it's a set with an addition and a multiplication. And the multiplication is commutative, and the multiplication such that there exists 1 in the ring with, like, x times 1 is 1 times x is equal to x. So an example of a ring would be the integers. Like, the integers are a ring, but they're not a field because we have 2 as an integer, but 1/2 is not an integer, and that's what the multiplicative inverse of 2 is, a half. So like good examples of fields would be real numbers, rational numbers, z mod a prime. That's pretty much it. Oh, complex numbers. Sadness. Yes, we probably should include complex numbers. That would be good.
Yeah, I don't think I've learned enough about complex numbers.
That's true. None of us have learned enough about complex numbers. So there's always more to learn about complex numbers. Or real numbers, for that matter. Okay, anyway. So you got this set of multivariate polynomials, and he says we define, for any f in, I probably should invent a name for this thing, but I'll write it down, k of x1, x2, xn. All right, for any multivariate polynomial, we define, he says df equal to, here it goes, a1, a2, an in k tuples over the field kn, such that what? Equals 0 is what I would have thought, but in fact, not equal to 0. So the complement of the locus of the zeros of f. And his next point is that he says, and now he makes some points. What's d of 0? Yeah, I heard the empty set. Do you guys agree? I want to put 0, I mean the 0 polynomial, right? F equal to the 0 polynomial. Feed any point to it. Can you get something non-zero from the 0 polynomial? I mean, no. It's a contradiction. There's no point which satisfies that condition for 0. So yeah, empty set. How can I get the whole space? How can I get all of Kn as D of something? D of what equals to Kn? Yeah, just put 1 there. So in other words, we're talking about f of x equals to 1. This x is a vector x, okay, but it's x1 to the x to the n. So yeah, that'll work because that's not equal to 0 for every point in Kn. So we get the empty set. We get the whole set. See where we're going with this. What else do we need? The question is, are we describing the open sets or the closed sets in a topology, right? We got choices. He says next, if, oh, he claims, now we should think about this. What if we look at df intersect with dg? What's that going to be? So df is n tuples that f of a is not 0. That's g of a not 0.
Is that the 0 locus of all four non-node interactive generated by F?
I think it's less. I think it's easier. I think it's just this. So if you think about, I mean, how does FG? This is just the product of FG. So like FG. Let's use A for a second here. Of A is f of A times G of A. I mean, you actually have choices here. You could plug in you could multiply the polynomials out and then evaluate at A, or you could plug in, you could evaluate and then multiply. I mean, they're equal in this context. So, but anyway, my larger point here is if either one of these is 0, then that means, let's see here. So if you suppose a tuple is in the left-hand side, it follows it's in the right-hand side. The other inclusion I'm not as clear on.
It has something to do with you can't have non-zero divisors, right? Because how would I know that f of a times g of a could not equal 0 even if f of a and g of a were not equal to 0?
So you're saying if I set this equal to 0, if these are both non-zero, if they were non-zero such that I got 0 there, that would say that there's 0 divisors.
I don't know where, but it's
Yeah, I think that's right. see, the theorem, I mean, definitely fx. If f is a field and we look at polynomials over the field, it's the integral domain. The question is, if you have polynomials over an integral domain, is it an integral domain? Like if you take a given integral domain, neither of you, you've had one. You've had abstract one.
Yeah.
So I don't know if this is a theorem that we talked about or not, but what if we have an integral domain and we look at polynomials built with coefficients from an integral domain? Is that an integral domain? Does it have zero divisors? Right? That's the question. No, I was about to use D. Bad choice. I, maybe. So is I of x integral given I is integral? And in fact, I think that's true because we prove that. You have to look at the leading, it amounts to looking at the highest. If you look at the highest term, if you had that the product of two non-zero things was 0, then you could focus your attention on the highest term in the two polynomials. It would if it multiplied to be 0, that would have to be 0, but that would imply that you had the product of two things and I being 0, yet neither one of them were 0, which of course is a contradiction to I being an integral domain. Why is this relevant? It's because remember that this, well, I'll just do it with 2. This we can look at as being so if k of x is integral, then k of x of y is polynomials over an integral domain, and hence polynomials in n variables by extension is an integral domain, which what you're saying is very relevant. The only way that this could be 0 is if one or the other of these is 0, which I think is that formula. Okay, so then here's the deal. He says basis equal to df I should have given this thing a name. Oh well. So if you let that be that defines a basis for a topology on Kn. What's that mean? That means that, what does it mean to be the basis? It means the union of things in there is again what? Well, first of all, those are the open sets by definition. Those are the basic open sets. And yes. How'd that go? Well, here, let me scribble down. Yes, I think there might be some more technical legwork to do before we've proved this is a legit basis for Kn, granted. Before I get to that, though, what would a closed set relative to this topology be? I mean, if you look at Kn minus df, what's that give you?